last semester you told me that you
Yeah.
something like that. I can't remember. Okay. Maybe you said you're going back.
Yeah, probably.
Do you have any questions about any of the problems I've put up? I'd like to do at least one. Anybody? Y'all got it, did you? You have the book, right? Any questions at all? I'm used to at least one or two questions, at least in most of the classes I teach. Let me ask you this, how many did them? I give you the solutions and everything, but if you haven't done them, I encourage you to keep up with this. This is a typical problem. People, first week or so, and they start getting behind, and then all of a sudden, the rate that they have to go to catch up is overwhelming. I'm just warning you about this, because I have too many people fail this class, and really in the summer failing, it's easy to do, because everything's condensed from 15 to 10 weeks. So by the time we're doing microwave design and everything, you're still trying to figure out how in the world you get reflections and things like that, and you're really in trouble. So, yeah, go ahead.
Can you explain why the frequency doesn't change between liquid and air?
Frequency will never change. Right? That's the one constant. Whenever you send an electromagnetic wave, wavelength will change, it'll attenuate in magnitude, but frequency never changes at all. One of the homework problems, can you give me one you want me to work? Anybody? Okay, you want to give me one?
I don't have it pulled up, but I can.
All right.
Sorry.
You have your book? Can you read me 631? Or that's short, that's 630. 611.
Yeah. So in a lossless non-magnetic material with epsilon relative equals 16, and then your H field equals 100 cosine, WT minus 10Y in the AZ direction.
Omega T
Yeah.
minus 10Y
Yes, sir. In the AZ direction, and that's in milliamps
milliamps
per meter. Yeah. And then it says determine the propagation velocity, the angular frequency, and the instantaneous expression.
And I assume it's non-magnetic?
Yes.
Sigma equals 0. So if you take a look at this, I want to go through, I want to make sure everybody understands how to do this without any kind of problem, because you can get stung so bad if you don't understand the basics. For this one, this is an H field in the time domain, correct? You'll notice the orientation is Z. Y'all follow me? The polarization is Z direction. Which way is it propagating, and how do you know? Take a look at it.
Right hand over it.
Take a look and think about it just for a second. Now, if you don't know, good. Form the question in your hand and we'll answer it. Do you know which direction it's propagating?
Not yet.
No. Do you know? Who knows? Anybody? All right, go ahead.
I believe it's the Y direction.
Why? You're right. Because what? That is minus 10Y, right? So first of all, we can say that beta here is 10. You all agree with that, right? The form of this is always going to be omega t minus beta times the coordinate, right? Now, if that's a plus, it's going in the negative y direction. We covered that. If it was a minus, it's going in the positive y direction. Y'all follow me? So a unit vector in the direction of propagation would be simply AY. Do we all agree with that? Everybody? Now, you follow me on this?
So say that again.
It's a unit, if it's propagating in the y direction, this is a unit vector. in the y direction. It has a magnitude of 1 and it's pointing in the y direction. Do y'all follow me on that, class? Now I want to put it in the phase. Well, let's see, if we have beta, can we get omega? You asked about frequency a second ago. I'm gonna show you. How do we get it? You're right. How about we go back to the definition of propagation constant, which is alpha plus j beta, right? That's equal to the square root. How many know what this is? I'm gonna write here. Anyone? I'm gonna start going after my students before. You should know this because I beat this into your head. Go ahead.
Be J omega.
You're right. It's j omega mu times sigma plus j omega epsilon. That's the definition, right? And that's from material parameters. Do you all agree with this, class? Now I'm going to start modifying it based on what is stated in the problem. It says it's lossless, right? Correct? If it's lossless, sigma 0. You agree with that, class? And also, if you look at this, that means this gamma is simply going to be equal to j beta, and that will be equal to, and take a look at this, I got j omega, so it would be equal to j omega comes outside times square root of mu epsilon. Do y'all follow me on this? And that means beta itself is equal to omega times square root of mu epsilon. Correct, everyone? Y'all follow me? I'm trying to be very clear about this. And this should be second nature to you. By the end of next week, this should be something that's automatic. You don't even think about it. That easy. All right, now, when we take a look at this, we have beta, right? We want to get omega. Beta is equal to omega, and square root of mu epsilon can be square root of mu naught epsilon naught times square root of mu relative epsilon relative. Correct, class? You all follow me? Now, take a good look at this for a second. We want omega, right? I have beta. I can say omega is equal to beta here divided by square root of mu naught epsilon naught, right? Mu naught epsilon naught, right? Divided by square root of mu relative epsilon relative. That's not very neat. Now I'm going to put in the values. Beta we said is 10, right? Now, what is 1 over the square root of mu naught epsilon naught? Anyone? It is the velocity of light, or the speed of light in a vacuum. It's 3 times 10 to the 8th meters per second, approximately. So this is going to be times 3 times 10 to the 8th meters per second. Then I have 1 over the square root of mu relative epsilon relative. Well, mu relative is 1 and epsilon relative is 16, so this is 4, isn't it, class? You all agree with that? Now, what's this going to be? That's 3/4, right? And it's going to be 3/4 times 10 to the 9th. It's going to be omega. Do y'all follow me? And what is omega in terms of f? This you should know from circuits.
2 pi.
2 pi f, right? So now if I can say this is 2 pi f, and therefore if I wanted, I could say frequency was equal to what? 3 over really 8 pi, right? Times 10 to the 9. And that would be in hertz, if I wanted the frequency. And I do, usually. Most of the time you want to make sure you know the frequency. But that, I'll leave it in terms of that, right? Does everybody follow me what I'm doing here? I'm just examining this, getting all the information. I've got the frequency, got omega, identified beta, direction of propagation. Next thing we're going to do is put this in the phasor domain, the H field. Now how do you do that? Do you remember? We talked about this. To put it into the phasor domain, and you can put a tilde over it if you want. I take the same magnitude, and it's 100 milliamps. We do milliamps per meter. Now I'm going to go ahead and do what? E to the minus j. We've identified beta as 10, right? And it's in the y direction, and it's AZ. Y'all follow me? That's the phasor form of that. Phasor means you get rid of the cosine term, you don't show any value of omega, and you express it in terms of e to the minus j, beta, z. It could have an e to the minus alpha if alpha was any value, but alpha is 0 because it's lossless. Do y'all follow me? Okay. That's the phasor. Now, next, How do I get the E field? In the phasor domain. Do you remember? Do you remember? These are two that I had 3 megawatts, so I'm gonna hassle them with this. Go ahead.
I don't exactly remember the equation for it.
You remember, how many remember me going over this? It was the trick, right? The trick, 2 tricks. Well, for E, it's 1 over eta, right? And then it's gonna be times a unit vector in the direction of propagation. Excuse me, for the E, I did that wrong. It's gonna be minus eta times the unit vector in the direction of propagation crossed into the H field. Do y'all remember that? Regardless if you remember it exactly or not, it takes a little time to get used to this. You all remember seeing it last class, right? And please come to class every day, because if you miss 2 or 3 classes out of a, say, a 2-week period, you're gonna be lost. Because we're gonna cover a lot of ground. We have to. It's 10 weeks, so we've gotta get through that whole into the book. All right, now do we know eta? What is eta, anybody? I'm gonna keep going after you guys. No, I mean, what do we call it, the term? Intrinsic impedance, right, of the media? What is the intrinsic impedance of the media by definition?
It's J omega mu over square
How
root.
about square root of J omega mu over sigma plus J omega epsilon? Isn't that right? That's the fundamental definition.
Oh, yeah.
Now, I'm going to modify it to account for it being lossless. Lossless means sigma's value is 0. Yes. All right, so I get rid of that. What else do you notice goes away? You see a J omega upstairs, J omega downstairs? They go away, don't they, class? You all see this? All right, so that's true. This becomes square root of mu over epsilon, right? Now, I always break out square root of mu naught epsilon naught by itself. I know that value is 120 pi, or 377 ohms. So I can say this is really the square root of mu naught over epsilon naught times square root of mu relative over epsilon relative. Now, mu naught over epsilon naught, square root of mu naught over epsilon naught is 120 pi. Do we agree on that? Make sure you know that. So it's 120 pi. Now, mu relative is 1, epsilon relative is 16, so it's going to be square root of 16 is 4. That means this is 30 pi ohms. Do you all follow me on that? Take a good look. Everybody with me? All right, now, after that, I've got my vector, I've got the intrinsic impedance needed, I've got the unit vector direction of propagation, I have the H field, correct, class? Now I can get the phasor form of the E field. And I can say the E field itself, the phasor form, will be equal to minus eta or minus 30 pi, right? Then it's going to be times the unit vector in the direction of propagation, which is AY. Right? Then I have to cross that into the H field, which is going to, instead of having 100 milliamps, I'm just going to put 0.1 amps per meter times e to the minus j times 10y in the AZ direction. Okay, do that for me. What do you see happening? I've got 30 pi and 0.1. That's 3 pi. Y'all, or it's, I'm sorry, it would be 3 times pi right here, and there's a minus sign, so minus 3 pi, right? Now what happens here? I'm going to have this e to the minus j times 10y here, and then I have ay cross az is ax. Do y'all follow me on that, class? Ax. And that's amps per meter. Now, I want to just tell you, that's absolutely correct. I can get rid of that negative sign by adding either a plus or minus j pi in here, all right? Because j pi is 180-degree phase change. It would account for that negative, leave it as positive. I'm going to leave it as negative for now. Now I want to go back to the time domain. What do I do? Remember, what am I really going to do to go back to the time domain? Now I have to introduce the cosine argument. right? This is the observable domain. I mean, we could measure this theoretically. So it'd be minus 3 pi, right? Now I'm gonna have a cosine of omega. I know what omega is, but let me go back a second. Here's what I'm really doing. I'm gonna say the E field, if I have the phasor version, is really the real value of e to the j omega t. Now I reintroduce the omega term times e in the phasor domain. That's the e in the phasor domain. And do y'all remember when we take the real part of this, we have a cosine plus j sine, we just keep the cosine. Do y'all remember this class? With me on this? Okay. So what's this gonna be? Magnitude's just gonna be minus 3 pi, left the negative sign. Then I'm gonna have cosine of what? The omega value I have is over here, which is 0.75 times 10 to the 9th to the 3/4 times 10 to the 9th t minus, it's gonna have the same beta, 10 y, right? And what direction is it, class? AX. And that would be volts per meter. All right. The homework I gave you should have made you familiar with this. It should have got you to a point where you can do this fairly easy. I mean, it made you aware of velocity. By the way, for this problem, I'm gonna just throw this out there. What would the wavelength be? Anyone? From that side of the room. You know? Anybody? Do you know this? Anybody? Everybody's looking at their notes. Anybody? Anybody in the class knows the wavelength is? What is the fun? Go ahead. You're
2 pi over beta.
yeah, wavelength is always going to be fundamentally 2 pi over beta. Do we have beta?
Yes.
10, right? 2 pi over 10. Do y'all follow me? That would be the wavelength. And to be frank about it, this kind of a problem, it should be something. I mean, come Monday or Wednesday at least, it should be something you look at it. All this is just second nature. You should have no uncertainties, no wonderment, I don't know. Because this is the kind of stuff you have to have. I think the German was fingerspritz, but you're German. Is that a word? Fingerspritz means you know the feel of it, you know it. Am I pronouncing that right? I got German in high school, but I don't. It's been a long time, and my German is so poor. Okay. By the way, I had a couple of German professors. And I want to tell you, there's a big difference in the amount of work given by an American professor in German. Orders of magnitude more.
Yeah, I had a German guy for calculus 2, I think. He was tough.
Talking about Eiffeltoilet.
What?
Eiffeltoilet.
Yeah.
Oh yeah.
It's the only class I was ever called stupid. Sit in the front. He's a physics guy. And he's talking, and I was tired. I think I was up half the night doing the project. Came in and he said, so how do you do this expansion? And it was fairly complicated things. Well, you're stupid. They're harsh. Okay. So,
So you said wavelength is 2 pi over beta?
Always.
Okay.
do you remember anybody remember how I proved that? I took the argument of omega t minus beta z, right? And I simply said, let t be 0, so I got rid of that. Now I have beta z. Well, when beta z changes by 2 pi, that's got to be 1 wavelength, that's 360 degrees. So I put beta times wavelength, that would be the delta, the z value, equals 2 pi. That's how you get it. All right. Okay, now I'm going to go through propagation and lossy media. Well, lossless media and then lossy media. But before I do that, according to the book, we have to talk about something called a complex permittivity. And the symbol is EC. And I'm going to try to make this easy to understand. My handwriting will get better. So let me just do this in a way that will try to make sense of everything. When we have curl of H equal to J plus the partial of V with respect to T, that's Ampere's law. All right, that's in the time domain. This is the most fundamental form of it. J is a real current. It has to do with electrons or some other charged particles actually moving through a medium. D is called the displacement current. The displacement current, nothing moves. Charge is displaced in, say, in the plates of a capacitor only because either there's negative or positive charge in the other plate causing a repulsion or attraction of the other charge. Do y'all follow me on this, guys? So when we have this, we also have the linking equations, J equals sigma E, and we have E, or I should say D is equal to epsilon E. And we have, by the way, this somebody recording this lecture gets you. Thank you very much. And we have B is equal to mu H. So I go back and I'm going to take this into the phasor domain first. The J would be sigma E, and then we have plus, and this would be epsilon times the partial of E with respect to T. Then I can group, I'm going to go ahead and put it in the phasor domain. In the phasor domain, it becomes sigma plus J omega epsilon would be times E here, and that would be curl of H. The term that's usually in the physics journals, geophysics journals and stuff, the curl of H is referred to as the Maxwell current density. It's the total current density. It combines both conduction and displacement current. So they term that Maxwell current density, but don't worry about that. The curl of H is this. Do y'all follow me? Now, when I think about this, that sigma, and I gotta be clear about this, the sigma term is associated with conduction, where if you could spray paint an electron or a charged particle and then watch it move, it will move through the entire lattice, or it will move about the media, the liquid or whatever, and get, if you had a battery driving it would go all the way around, back through the battery and keep going. Do y'all follow me? You could follow it. That's charge moving. When you have charge that is bound, do y'all remember this when you had EMAG 1? Bound charge, in other words, if you just had some sort of a dielectric and you apply electric field to it, the charge expands somewhat or contracts. There's like springs holding the plus and minus centers. Do y'all remember this, class? That movement of charge does cause charge to move, but it's localized. It can't flow. It's just going to move back and forth and cause heating. Do y'all follow me? That heating that happens now, whenever you have, like you have microwaves, right? You have water in there and stuff like, you put anything with water in there, because water itself is a molecule that is polarized, and you apply microwave frequency, you're going to heat this thing. The heating isn't because there's, at least, well there could be, but the heating is usually the localized molecules are just spinning around and they're causing thermal heating by agitation and friction motion. Do y'all follow me, class? So what we do when we talk about a lossless, I should say, a low loss dielectric, right here, we first usually assume sigma is 0. Forget conduction. We're not talking about anything to do with conduction. Now, Whitmer's book doesn't do it quite this way. What we do is this. We say that we're going to account for all losses by introducing a complex permittivity that is in the phasor domain. Remember that, not in the time domain. The complex permittivity is equal to epsilon prime minus j epsilon double prime. And I'm going to show you why this works. I hope this doesn't seem too disjointed. I start from here, went to here, all right? Now I just want to make sure you understood from here to here. We're going to get rid of this term and we're going to focus on this term to account for all losses due to that frictional heating in the dielectric. Do y'all follow me? So we introduce this term, it's called the complex permittivity. And we find out when we put that in there, we get curl of H. Now sigma 0 on this one is equal to J omega epsilon complex times E. And that's equal to curl of H is going to be J omega epsilon complex is epsilon prime minus J epsilon double prime times E. I'm just taking this and sticking it into this equation. Y'all follow me? Now, I get down to here, and now I'm gonna just expand this. So I have curl of H is equal to, and I have J omega epsilon prime times E, and then I have plus omega epsilon double prime times E. I'm gonna stop there for a second. Y'all follow me? Can you read it? Okay, now, this term is the same as this term right here would be. It's just equal to epsilon relative, and I'm going to rewrite it here. Now I have curl of H is equal to, put it on this side because you're used to saying, plus J omega epsilon relative to epsilon naught times E of this term, the omega epsilon double prime E. This accounts for losses. All right? And here's how. You see, when we look at this curl of H, we have sigma times E by itself, right here. If you just take a look, sigma E. Well, sigma is strict positive. I mean, it has no imaginary component. You follow me? Now, if you look at that, it's identical to omega epsilon double prime in terms of its position in the equation. Now, what it's really saying is this accounts for all losses, dielectric heating losses. And there's something else, we didn't get to power yet, but when and I'm gonna expand this again, I'm gonna say if I have sigma E plus J omega epsilon E equal to curl of H, if I take that and I wanted to see how much power was being dissipated, I would take this quantity, you don't know this yet, and dot it with the E field. And that would be the power dissipation. Now, there's more to this, but if you take a look at this, just think of the units. The sigma E squared there, it's a power dissipation from conduction current. This, because of the J right here, will not cause any power dissipation at all. Well, I'm gonna have to wait on some of this, but y'all know how a capacitor has the the voltage and current are 90 degrees out of phase when it's driven by a sinusoidal source. Same with an inductor. The current and voltage are 90 degrees out of phase. How much power is dissipated by either of those elements? Does a capacitor dissipate power if it's an ideal capacitor? No, it stores energy and you can get the energy back out. It never dissipates power. By dissipation, it means turns, say, the actual electrical current or voltage difference into heat. It doesn't. Do y'all follow me? Ideally, you charge a capacitor up, all the energy you put into it, you can get out of it. You can short a resistor across it. Do you follow me on this class? An inductor too, it's a storage element. All the current that's driving the magnetic field around there and causing the energy to be stored, you can get all that energy back out. But you can't get any energy out of a resistor. When you drive a current through that as it's dissipating heat and stuff like this, that's gone for good. Y'all follow me? All right, now, this is an energy loss. It's thermal heating. Just think of it that way. That term is related to thermal heating. You'll find out more about this when we get into power dissipation. That is energy storage, if you will, that term. Now, it's necessary to I'm trying to introduce this in a way that at least makes sense. This is the reason we're doing it, all right? And when we talk about dielectric materials, I mean, what are some of the dielectric materials you think of? Anybody? What's a good dielectric? Styrofoam? Is that a dielectric conductor, or you don't know? Isn't styrofoam a pretty good insulator? What about rubber?
Yeah.
Pretty darn good. If it's an insulator, it's a dielectric, right? Mica, right? As a matter of fact, anything that won't allow current to conduct is a dielectric. And it's real important we have an appreciation for this, because with dielectrics, we use dielectrics to insulate wires, right? We use dielectrics inside cable when we're talking about coax cable and things like this. But there's two things about a dielectric that are important. One is that it has a voltage breakdown that's low. In other words, I shouldn't say voltage, a electric field breakdown, sorry, that's high. Let me explain that a little bit. We're here, it's air in this room. When I say the electric breakdown potential, I'm saying something would cause an arc. You know what lightning is, or you've seen sparks, right? That's an electrical breakdown of the atmosphere. So how large does the electric field have to be in this room before you get dielectric breakdown or an arc? Does anybody know? I mentioned this in you guys' class, but I probably don't know.
Yeah.
Anybody want to take a guess?
What was the question again?
How large would the electric field, if you could impress an electric field, have to be before you get electrical breakdown in this room? I'm saying about air, normal air. It's about 3 million volts per meter, right? 3 million volts per meter. Now that sounds like a lot, but that's per meter. When you get down to something microns of spacing, or tens or 20, even tenths of a millimeter of spacing, that's not much. That's a voltage difference of only a couple of volts. Do you follow me? So the big thing is, have you had your FET transistor course? Have you had transistors yet? If you had, you know there's MOSFETs, right?
Yeah.
The FET is basically a capacitor. You've got a dielectric, you've got a plate area, and it either pulls up a channel or it represses a channel, right? That dielectric right there needs to be able to withstand a huge electric field difference, all right? So the dielectrics they choose have to have a breakdown potential much, much higher than air. Orders of magnitude. Instead of 3 million volts per meter, it may be 300 or even 3,000 million, if you will, 3 billion volts per meter. Do you follow me? And that's what's important with dielectrics. But whenever you have a dielectric, as good as it gets, there'll be loss. So every time you have a time varying current or a time varying voltage on it, it's going to dissipate some heat. Just keep that in mind. Let's take a look at how we actually describe these things graphically. When we take a look at the complex permittivity, usually what they do is this. They're going to say this is going to be the imaginary. We're going to take a look at a graph of curl of H. So we know that that's equal to this right here. We take a look at curl of H, we're going to put the imaginary component here, and we're going to put the real component here. Try to understand it. So up here, we would have the imaginary component would be, the magnitude would be omega epsilon relative epsilon naught times E, and the real component would simply be omega epsilon double prime times E. And then we graph this. And we're going to see that this is called a loss tail. The symbol for this is gamma. I'm going to simplify this in a second. This is in your book. I don't know the page number. Give me 1 second.
So I was going to ask you
This is on page 333. Go ahead. What?
so the second question you have there for curl of H, is that supposed to be?
This?
Yeah, is that's supposed to be J omega times complex permittivity times E? With the thing
This
that's
is-
circled there?
Let me rewrite it. This is the standard form right here we're talking about. Curl of H is normally given as sigma E plus J omega epsilon. This epsilon is just epsilon relative epsilon naught. We didn't introduce complex permittivity. The way they account for the loss, they don't want to put a sigma value in here, even though they could. What they'll do is they'll give it a complex permittivity value here, so this epsilon double prime, when you go ahead and do the math on this one, it breaks out something that's effectively like sigma. Let me start right here. Like here, this is really signal, but it's not. All
Okay.
right, because it has the same exact effect on the equation. It's a lost term, but it is not relative to real conduction. Do you follow me on this, class? That has to do with just bound charge dissipating power or heat.
So that's what complex permittivity does, is it basically.
It accounts for the effects
reflects-
of losses
Okay.
that would otherwise have to be accounted by conductivity. And this is the
Okay.
way they actually, the material science people do this. So typically when they talk about this, if I'm plotting this versus that, you realize that we can get rid of the E field. It appears in both, right? When we take a look at this, the only thing that matters right here is epsilon relative to epsilon naught and epsilon double prime. And if you take a look at this, actually, you could just call this epsilon prime here. This would be, I should do it this way. What I'm really doing is showing you this. I'm showing you a plot where on this axis I have epsilon prime, and on this axis I have epsilon double prime. This is on page 333 of your book. Now, there's a way to go ahead and they quantify the value of this is they talk about something called the loss tangent. And that's, well, actually, the loss tangent, I think in his book, yeah, he uses, unfortunately, he uses this. And that means the tangent of that is equal to epsilon double prime over epsilon prime. Let me just talk about this for a second. In the book, what you're going to see is a plot of epsilon, really, epsilon prime on this axis and epsilon double prime on the vertical axis. So if you think about this, it means this length from here to here is epsilon double prime, and we know opposite over adjacent is tangent of the angle. Do y'all follow me? So when you look at material parameters and they talk about dielectrics, what you'll see is that if you have a given frequency or frequency range, they will have the loss tan, all right, or really, and by the way, do y'all know the tangent of a small angle is about the small angle in radians? Do y'all know that, class? Like, tangent of x is about x if x is small. Do y'all remember that from your math classes? That has to be in radians. But this right here is called the loss tangent, right here. That really loss tangent is this. As such. And normally what they'll do is give you the value for epsilon relative, which is, and that means you have your epsilon prime, because epsilon prime is simply equal to epsilon relative epsilon naught. So they'll give you this, and then they'll give you the loss tangent, so you can find epsilon double prime. Y'all follow me? And I'll show you this in the book. This is important. So, back in the book in the appendix. Trying to find it. If you look on page 625 in your book, they have properties for selected dielectrics. And you can look at mica, polystyrene, quartz, silicon, and you'll see the values for the loss tangent only at one frequency, at a megahertz. I want to say this, that usually when you're doing any kind of real engineering work and you need to get a good dielectric, you gotta make sure it's gonna work over the frequency range you're gonna operate. They'll have the actual loss tangent as a function of frequency, and you'll see it change. Epsilon relative will stay the same usually over a fairly wide range of frequencies. But the loss tangent will change, and you have to be aware of that. All right, now this is, I know it's a bit material science stuff, but you have to be acquainted with this as you go on. Okay. So really, I guess, in summary, I can say that omega epsilon double prime is kind of like sigma. Right? It's got the same effect as sigma, only it's not. You follow me on this, class? And you have to be aware of that. And sigma's a property that has to do with dissipation of power. So now, after that, we talk about propagation of good conductors.
On your graph, is gamma the same as E double prime? Is it?
What I'm saying is this is the angle right here.
Okay.
Yeah.
On the tangent fullness, that's not have to be done in meters.
No, I mean, you can take the tangent of this, as long as, if you knew it was in radians or degrees, you have to know what it is. But usually what they do is state what this is. They'll give you that value, tangent. So you know, and it's the ratio of epsilon double prime over epsilon prime. It's usually like 10 to the minus 4, 10 to the minus 5, 10 to the minus 6. Something very small. Okay. With me on this? Do a few problems. Did you have lost tangent in EMAG 1? I think so.
Yes.
We did? Did we?
Kind of touch base on it, yeah.
I think we did, but I don't think I really went into, I might have gone into this level of detail. I don't remember exactly. Usually in EMAG 1, because it's electrostatics for the most part, you don't think about loss tangent. Until chapter 5, you don't have time varying effects. Okay, next. It's going to be propagation in good conductors. This is important. A lot of things change. So if we have good conductors, what are some good conductors, everybody?
Auburn.
Very good. Copper is probably the one we're most familiar with. Anything else?
Gold.
Anything else?
Aluminum, kind of.
Aluminum?
Not as good.
Right. Silver, I mean, we could go on with a whole list of things, right? Frankly, any metal is a good conductor for the most part. I can't think of a metal that's a bad conductor, and I mean electric conductor. Steel, aluminum, platinum, all of them are good conductors, very good conductors. Believe it or not, seawater is a pretty good conductor relative to what's around it, air and stuff like this. Seawater, salt water, let me be clear about that, is a really good conductor, pretty good conductor, super, pretty good. But when we look at these good conductors, and we talk about the effects on both the propagation constant and the intrinsic impedance, it's very important. So when we talk about a good conductor, what we mean by this is sigma is much, much greater than omega epsilon. And this is not a complex permittivity. This is omega times epsilon relative epsilon naught. You all follow me, class? So anytime this is the case, say an order of magnitude or better, then when we look at the propagation constant, which is alpha plus j beta, we find out that that's equal to the square root of j omega mu times sigma plus j omega epsilon, right? That's technically what it is. But because it's a good conductor, and this is true, sigma is much, much greater than omega epsilon, I can get rid of this. I can say this is approximately true. Do y'all follow me? I'm already stating that omega epsilon is much, much, much less than sigma. Sigma dominates, okay? So this is about what this is going to be. Now if I look at that, that's equal to the square root of j times square root of omega mu sigma, right? Okay. So what is j? By the way, if you wanted to, you could use this camera to record right here, but you can use your phone.
I tried it, but I didn't want to get in everyone's way.
Oh, you can do it. Don't worry about it. This is summer. We're relaxing. So when we talk about J, let me do it right here. So everybody can see. So what is J? What does it really mean? Well, first of all, it's not in the observable domain. All right, you don't observe J's in time domain. J is something that is really a mathematical construct, right? What is it? Technically, anybody? Square root of -1, right? Mathematicians created this. That's one way to express it. Do you all remember that? All right. What else is it? Well, it's also e to the j pi over 2 or e to the j 90 degrees. Do you all remember that, class? E to the 0 is 1, that's strict real. E to the j 90 degrees or pi over 2 is just j, isn't it, class? What's this value? What would e to the j pi over 4 be? That's 45 degrees. How would you do it? Anybody? If you wanted to know what the real and imaginary value is, how would you get it? Anyone? Go ahead. Do you guys remember Euler's identity? EU? If we used Euler's identity on this, what would it be? It would be cosine of the angle pi over 4 plus j sine of the angle pi over 4. And what I'm really saying is e to the j theta is cosine of theta plus j sine of theta. By the way, these are things it's assumed that you're very familiar with this by the time you're at this level in electrical and computer engineering, these type of identities. So let me keep going on this one. That means e to the j pi over 4 is, well, what's the cosine of 45 degrees anyway? 1 over square root of 2, right? What's the sine of 45? Same thing, isn't it? Same thing, amazing. So I have 1 over the square root of 2 times 1 plus j. That's what this is. Now, if j is equal to e to the j 90 degrees, or pi over 2, what's the square root of j? Isn't that the same thing as j to the 1/2 power? And isn't that the same thing as e to the j 45 degrees, half the angle? Can you all see that? You with me on this, class? So come over here with me. That's the reason I broke out that square root of j. Square root of j is just 1 plus j over the square root of 2. Follow me, everyone? So this becomes, I can say that gamma equal to alpha plus j beta is equal to 1 plus j over the square root of 2 times the square root of omega mu sigma. Now I'm taking the top and putting it down here. I'm replacing j with its definition, square root of j with the definition, okay? Now what they typically do is this. I'm going to replace omega in that equation with 2 pi f. And then I'm going to bring the square root of 2 inside that square root operation. So I get this is equal to 1 plus j times the square root, omega is 2 pi f, times mu sigma over 2. Y'all follow me? I'm just going ahead and I'm modifying this so I have everything under the square root. And one of the things you see is the 2's go away. Hopefully you do. So I get rid of them. And now I have this. I have square root of pi f mu sigma times 1 plus j is equal to alpha. Equal to gamma. That means alpha is equal to beta in a good conductor is equal to the square root of pi f mu sigma. This is important. This is always true for a good conductor. Alpha is beta. So anytime you see an equation, a mathematical statement about something, if you see what alpha is equal to beta, then you know you have a good conductor. Follow me on that, class? All right, next. After that, we go ahead and we get the intrinsic impedes. Now, the intrinsic impedes the square root of what? J omega mu over sigma plus J omega epsilon. That's the definition we use if we're in a phase domain. But if we have a good conductor, what happens in that equation? Take a look. Sigma dominates, right? The only thing we do is get rid of this junk, right? With me, class? I just erase it, right? You can ignore the J omega when it's added to sigma because we're assuming it's so much less. Follow me? What's this gonna be? Well, I'm gonna get the square root of J, which is just e to the J pi over 4. I can leave it like that. That's gonna be 1 plus J over square root of 2. And then I can have square root of omega times mu, right, over sigma. A little better job than that. Square root of omega mu over sigma. That's the intrinsic impedance. Now, generally speaking, that is very small with respect to 125 or 8 and 9. And I mean 5, 6, 7 orders of magnitude less. Do you follow me, everyone? And this would be for a good conductor. That's in a good conductor. Now, what happens if we're in a good conductor and we talk about phase velocity? So what is phase velocity? Fundamental, do you remember? We did, I got that. How do we get it? Go ahead.
Speed of light.
What is, how do we get phase velocity? What's fundamental? You remember there was a cosine of omega t minus beta z, right? When you took that, omega t minus beta z, set it equal to the phase, and it took a derivative of that, set it equal to 0, you get a dz dt, which is the phase velocity, which is omega over beta. Do you remember that now? Sure. So phase velocity is fundamentally omega over beta. Right now, I'm going to use, we're in a good conductor, so we take a look at this. I think I put down a second ago, right there, beta and alpha are the same. So if I look at this, omega is 2 pi f over beta, there's beta. Beta is the square root of pi f mu sigma. Now I can mess with this all I want, but I can see one thing that happens. I can leave the 2 out the front. Then I can pick, under the square root, I'd have pi here. I would have over, for pi f, would be up there, and then I'd have divided by mu sigma, would be the phase velocity. Y'all follow me on that? I've just taken omega is 2 pi f, beta is square root of pi f mu sigma, and I've combined in terms. Do y'all see what I've done there? Let me just show you an example of how crazy and how small the phase velocity is in good conductor relative to the speed of light. Let's do an example for copper. So if we have copper, anybody remember what the conductivity of copper at room temperature? Large would be a good word, but it's what, 5.8 times 10 to the 7th, 1 over ohm meters. Do you all remember something like that? Did you have that kind of information before? EMAG 1 or any of your other classes? How many remember hearing that before?
I think so.
Sure, conductivity is a very important thing to understand. So this is for copper, it's 5 times 0.8 times 10 to the 7th. So now let's say we're at a frequency of omega is equal to, or better yet, F is equal to 10 to the 8th hertz. All right, just shy of a gigahertz. It's 100 megahertz, right? What is this? What's the phase velocity going to be? Take a look. And let's assume that this is copper, so mu relative is equal to 1. Now I have 2 times square root of pi times 10 to the 8th over mu, just mu naught, which is 4 pi times 10 to the minus 7th. times sigma, which is 5.8 times 10 to the 7th. Now take a look at that. And y'all see what I've got there is really 2, right? Then it's going to be times the square root. The pi's cancel. I have 10 to the 8th upstairs. I get 4 downstairs times 5.8. And the 10 to the 7th, minus 7th and plus 7 cancel. I get this, which means I have 2 times 10 to the 4th right here over the square root of 4 times 5.8. Now, I want you to take a look at that. You all see that that's going to be much, much less than 10 to the 8th? I mean, what's the speed of light in a vacuum again? About 3 times 10 to the 8th meters per second. This is less than 10 to the 4th meters per second. Y'all see that? That's 5 orders of magnitude less. So this is important. If you had a solid chunk of metal and you were propagating a wave this way, it would attenuate very rapidly. But the propagational speed becomes almost, pale comparison to the speed of light in a vacuum. Y'all follow me on that? Matter of fact, we had a professor here years ago named Dr. Shumpert. He used to say that, at a given frequency, I can run faster than the speed of light can propagate in that medium. That's how slow it can go. Right? Now, I gotta say this, that doesn't mean that when you have a wire, that's the speed of propagation in a wire, so don't mistake me. When I say if you had a solid cord wire, the propagational speed of the wave towards the center of the core of that wire is that fast. Along the wire, it's about the velocity of light, or the dielectric is the thing that limits it. Do y'all follow me on that? So I want to make sure I don't confuse you. This has to do with a wave propagating into the actual metal, not on the surface of the metal. And a nice working duct would be the wave was there. So that's propagation in good conductors. And now we're going to talk about one thing that's real important called skin depth. And skin depth, by the way, these terms come about because they sort of clue you into what's really going on. So when we have metals, and I want to be clear about this, these are good conductors we're talking about right now.
Can you leave that? That's a little bit there.
All right, when we have good conductors still, and we look at the effects of a good conductor, or what happens when you get a high frequency, and how we go about more or less creating terms that are useful in actually solving problems quickly. First, if we have a good conductor, we know alpha is about equal to beta. We know that. Is equal to the square root of pi f mu sigma. We know that. That's given. We also know that the electromagnetic field equations will always have some virtual magnitude that's given at a point, and they'll propagate, if it's propagating to the right, with an attenuation constant there. I'll have e to the minus j beta z here. Call it in the ax direction to be consistent with Dr. Wentworth's book. So that's a way of traveling in the positive z direction, but its polarization is in the x direction. And if we graph that, just the magnitude e versus z, it would do this. It would come down, and this would be proportional to e to the minus alpha z. Y'all agree with that, class? Follow me on that? I'm just taking a look at the magnitude. This is going to cause the thing to decay as it goes through, right? The larger the value z gets, the smaller the value of this times epsilon naught is. So it's really got an envelope weight on it. So what they do is say this. They create a term called skin depth. Unfortunately, it has the same symbol as the lost energy. So this is the skin depth. What is the skin depth? It's the point right here where e to the minus alpha z goes to e to the minus 1. Y'all follow me on that? So it's when the argument of this exponential becomes minus 1. Follow me? Now that's the value. That's not actually shown where it should be. It should be about there. And this should be the skin depth. This is the value when you have e to the minus 1, or about 0.33. It's about 0.33 right there. So it's about 1/3 of the value of its peak. Y'all follow me? We term that the skin depth, and the skin depth is given as, if you look at this, since I have e to the minus alpha z equal to e to the minus 1 at a skin depth, that means alpha times the skin depth, that's the symbol for skin depth, is equal to 1, or the skin depth is 1 over alpha, or the skin depth is defined as 1 over the square root of pi f mu sigma. And that is the definition of skin depth right there. How many have heard that term before? Anybody? Skin depth? Okay. And it's very, very important to understand that. Now, for good conductors, it's critical to know that term if you're talking about the resistance of wire, the AC resistance at AC frequencies, high frequency. So now we're going to take a look at how this affects things. Okay. So if I have a standard wire, like such, and this wire has an area A, say it has a radius small a, and the area therefore would be pi a squared. And we've got a length L. And I asked you what the resistance of this wire would be if current was fed it, you had a voltage here. And you wanted the resistance of this wire. Now, the way I'm just trying to draw you a wire, but I've exaggerated the actual radial size of it enormously. But if you take a look at this, if it's solid copper or something like that, it's constant cross section. Do y'all remember that in class? This is just a long, solid piece of copper, something like that. You want to know the resistance from here to here. Well, the DC resistance is always proportional to the length. The longer the wire, the more resistance, right? It's always inversely proportional to the area. And it's always inversely proportional to the conductivity. Remember this class? Now the area for that one is pi a squared by sigma. Y'all follow me? When we all of a sudden try to drive current through this, but it's not with a DC source, but with an AC source. And we have some V here, some V naught cosine of omega t, or we drive it at a given frequency, then things change. And I'm going to show you how they change on this board. So, I hope you can see this. I'm trying to show you a wire with a radius of A right here. A is the radius. So we come over here, we're just going to take a look at the cross section of that wire. Here I have radius A, area is pi a squared. Now, when I have a high frequency source being applied to this, I have something called the skin depth that we talked about, which is equal to 1 over the square root of pi f mu sigma. And if the skin depth is much less than the radius A, then what happens is this. All the current that's actually going to flow in this is going to be constrained on the surface. So instead of flowing evenly over the cross section, it's going to be contained within 1 skin depth of the surface. Do y'all follow me? No current will flow in the core of that. It can't. And if you think about it, remember how I told you the electric field propagates towards the center of the wire or core? It basically shorts out by after 1 skin depth. And this is, what I can tell you is this is a very accurate description of what's going on. There's no uncertainty about the values I'm about to show you. So now all the current has to flow through just that surface I've got in green. You all see it? And what's that surface area? And this is what we call I call it the effects of high frequency on the area. Then that area, you might say HF, high frequency, would become what? Well, you would take the value of area of the entire cross section, which is pi a squared, right? And then you'd subtract from it the value of the area here, out to the radius A minus the skin depth. You follow me? The remainder is what's in green. So it'd be minus pi, and this would be A minus the skin depth squared. This would be the area that the current's flowing through, the high frequency current, if this is true. If all of a sudden the skin depth is much less than A. So now I have pi, right? A squared minus A squared, right here. Then I have minus skin depth squared, and then I have plus 2A sigma. And I can see the A squareds go. And I have pi times 2 times the radius times skin depth minus del squared. That's the new high frequency area. And that means the resistance, the high frequency resistance, or the AC resistance, as Wentworth puts it, will be still proportional to length, and it's still inversely proportional to sigma, but now the area is significantly reduced. As a matter of fact, typically, since sigma is much, much less than A, this term is ignored. Y'all follow me? If the skin depth is much, much less than A, then squaring that value and taking a look at the value of this versus that, this is insignificant. This is dominant. So then this becomes simply 2 pi A skin depth. It's much, much less than the area or the effective, the area would be for a DC source. Now, something I gotta tell you, the way I like thinking about this, because people are always, how do you remember all this stuff? You always, first you work with it so you don't have to worry about memorizing. You never worry about memorizing. You just use this stuff over and over again, it's ingrained in you. If you just cut that right here, or cut it in one spot, and then cut it and then unroll it, you get something that has the perimeter of the wire circumference, which is 2 pi times A, right? That way. And then this would be a skin depth line. Y'all follow me? Well, what's that area? Well, it's skin depth times 2 pi A. That's an easy way to think about this. That's what that is. So that's the AC resistance for a wire. And I'll tell you one other thing about this. Whenever the reason skin depth becomes important is if we have a standard coaxial system, I'm going to move this board here. we have a system with an inner core and an outer core. It's got some thickness, I'm exaggerating size around it, but something like this. Say the inner radius is A, and this is B. Hope you can appreciate this. This is cutting a coax cable right in half, but it's not your standard coax with just thin aluminum mesh on the outer part. This is solid pipe. So I've got a solid piece of pipe here, and it's surrounded by a solid piece of pipe there, right? Now, if you want the resistance per meter of this, this would be like cutting something and looking right down the barrel, as it were. When I drive plus to minus voltage on there, I'll get if it's a skin depth that's much less than 8, then I get all the current is constrained here, right? But remember, anything that flows down has to get back if you have a differential input. That means it's going to flow back, and there will also be a skin depth here that it'll flow through. Follow me on that, guys? Now, the total resistance per meter, just think about any kind of like a coax cable. You got current going down one, coming back the other, right? If it's going down the middle or the core, it's coming back on the sheet, the outer sheet. It has to if it's differential, right? And all our sources are always differentials. When we have extension cords, communication cabling, we have differential inputs. So they can.
So how come the skin depth is interior on the outside?
Because the electromagnetic field is actually bound between these two. Right?
Okay.
And there's no electromagnetic field out here. I've tried to make this clear as I can, all right? It's just short, there's nothing going to be out here that's measurable theoretically. This is a very long piece of pipe. I cut it in half and I'm looking down the barrel. So if I wanted to know the resistance per meter on this, I would find the AC resistance of the inner core. You follow me? And I'd have to add to it the AC resistance of the outer core. You follow me? They're not in parallel, they're in series, because whatever flows down that way flows back that way. So you would say the total AC resistance would be the AC resistance of the core plus the AC resistance of that outer sheath, but it would have to, you could do it per meter. And the materials could be different. Okay, I'm about out of time, but I'm going to tell you this. So when I worked on my master's work, I did plasma etching and reactive ion etching. And they had about, it was a 1,000-watt system. You all know what a plasma is? I mean, those lights have a plasma. It's basically an electrified gas. The reason they did that is because when they electrified certain gases that had fluorine in it caused something, a chemical, it's just like hydrofluoric acid, and it would etch through silicon. So they were used for really VLSI manufacturing. But what I noticed is all the piping was hollow. All the piping that connected the power source and stuff was hollow. This is a 13.56 megahertz system. And the reason is skin depth. If they had a solid piece of aluminum, they wouldn't get any better conduction properties than this hollow one that's a couple of skin depths thick on the outside. Y'all follow me? Then what they did is ran water through the center of that to cool it. So they had a refrigerant because things get hot and you've got to conduct heat out of it. So they actually used the inner core to run water. Another thing about this, you know these, and I'm not an expert on this, I could be wrong about some of this. You know the cabling that's used by the power companies, these high tension wires that are very large voltages, right? So they don't have to drain, they have a lower current capacity. Well, usually the core of those are steel or something. And then they have copper surrounding it because they would never get the tensile strength they needed if it was solid copper. They have to have something there that actually has got some strength that will not rip apart. And I got other stories for you about the crazy stuff I did with a guy from MIT with trying to trigger lightning with wires, but probably like another day. I think that's about time, but do you have any questions at all?
Is it possible for skin depth to not be significant? Well, I guess if you're low frequency.
Just get low frequencies, all of a sudden skin depth could be miles.
So then
we ignore it.
Yeah.
Then it's just like a DC resistance.
Oh.
All right, did you understand today's lecture? I'm going to ask you one thing. Please keep up with this, because I can tell you right now, I'm just looking at the class. I know it's only the second day. but I have a feeling a lot of you probably didn't, and you'll get swept under. I'm telling you, by the third week especially, you won't be able to catch up, because it's gonna move a lot faster. And people ask me, what's the level of difficulty in summer courses? Usually they're much harder, not always, but usually they require more time, and unfortunately, more people fail. Usually. I'm just saying, it's unfortunate, so I'm trying to